I will give you guys access to the final exam. I'll post it on D2L, and I'll post a copy to Discord so you guys can get started on that. Since we don't have any other classes afterwards, Katie is not going to be holding her help session today. Also because attendance on Thursdays has been very, very poor. So if you guys need any, give me 1 second. Let me. Um, okay. So yeah. Anyways, as I was saying, today we're gonna just do a little bit of review before the final exam. Um, and we'll sort of go over some topics. Then I will hand out the exam. If you guys have any specific questions that you want to see from the review sheet or anything like that, we'll take some time to talk a little bit about those types of problems as well. Additionally, since we're not doing feedback forms this semester, I am thinking about doing a quick anonymous feedback form through like Google Forms. It's totally optional. There's no requirement for you guys to fill it out, and it's up in the air whether or not I actually put that together or not. But it's always good to get feedback on classes, and I'm anticipating running this class again in the future, and it would be good to have some ideas on what I can improve and what worked well for people. So. Regardless, let's go ahead and jump into the review. And as usual, I kind of just want to sort of recap the semester so we can kind of take a look at it and see all the stuff that we have actually learned and covered this semester, because there is actually quite a bit of it. So we started this semester with limits. And limits we sort of talked about in a lot of different senses. We use them a little bit as sort of background for everything that we did. They were how we defined what a derivative is, etc. So you're probably going to run into some limits on the exam. I don't know how much I'm going to be diving deep into the theory on limits and those sort of things or continuity, but these are things that should always be in the back of your mind when you're dealing with these types of problems, right? So we will, with limits, we talked about continuity, the intermediate value theorem, and definition of the derivative. If you remember, the derivative was actually defined using a limit initially, right? And there's more stuff in here, but these are sort of some big takeaways that are definitely relevant later on. After limits, we sort of dove into doing derivatives, and the bulk of this class was concerned with differential calculus. So derivatives, power rule, product rule, quotient rule, chain rule. I used a slash for the first one of these and then used commas for the rest, so let's turn that into a comma. There's also trig and inverse trig derivatives, and exponential / logarithm derivatives. And also implicit differentiation. As a technique, right? Implicit differentiation is what we use primarily to solve related rate style problems. When it comes to derivatives, we talked a little bit about some of the theory and application. So things like differentiability implies continuity. Um, things like increasing, decreasing, critical points, concavity, and points of inflection. Um, local and global extrema. So this includes, I guess, what I would call the closed interval method, the first derivative test, which, if you remember, was basically a sign chart, and the second derivative test. Linearization, slash linear approximation. These are all things that we use the derivative to either show or to apply to something, right? Oh, and the mean value theorem lives in here somewhere too. Probably with differentiability, actually. And then at that point, we moved on from differentiation to integration. So we kind of put different derivatives on hold, but we would come back and use them later. You need derivatives in order to deal with a lot like the U substitution method. You need to be able to do derivatives to figure out how to apply U substitution. And we first started by talking about Riemann integration. I suppose I could write down at least a couple formulas. I'm going to jump back up here. Definition of the derivative, remember that this was f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x divided by h. And similarly with Riemann integration, we got that the integral from a to b of f of x dx is equal to the limit as big N goes to infinity of the sum from n equals 1 to big N of f of x sub n times delta x, where delta x is equal to big N over b minus a, and x sub n is equal to a plus n delta x. And we had some summation formulas to go along with this. Katie, do you remember off the top? Well, it's actually in the Discord. So these are on page 263 of the textbook. If you've forgotten them. Yeah, it's and luckily you guys get to use the ultimate cheat sheet on the exam because there's no reasonable way in which I could prevent you from doing that. So hey, open note exams, aren't they great? Um, doing everything open note. I'm actually not allowed to do that, unfortunately. So, um, what am I going to say here? All right. So after we did Riemann integration, which was, same way we did definition of the derivative first, I made you do it the hard way. We did Riemann integration first. I made you do it the hard way, and then we talked about the fundamental theorem of calculus. This was a two-parter. So part one says that basically what it says is that um, if big f of x is equal to the integral from a to x of little f of t dt, then big F prime of x is equal to little f of x. Basically what this says is that if you have an integral valued function, the integral from a to x of f of t dt, then if you take the derivative of that, you just get back the function you started with. This sets up integrals and derivatives as inverses to each other, right? And part two is sort of the part that gets all the glory. It's the one that shows up all the time and we use it all the time. It actually tells us how to evaluate definite integrals. The integral from a to b of f of x dx is equal to big F of b minus big F of a, where big F of x is equal, the derivative of big F of x is equal to little f of x. That is, big F is an antiderivative of little f, right? So essentially, this is what enabled us to do derivatives the easy way. And in order to do derivatives to do integrals the easy way, and in order to do integrals the easy way, we needed to take a step back and talk about anti-differentiation. And we started with a couple of basic ones, just like what's the antiderivative of 2x? Well, x squared is the derivative of x squared is 2x, so the antiderivative of 2x is x squared, right? So we saw a power rule for integrals. We had a couple properties of integrals as well. Sums and constant multiples in particular. And then we kind of hit our one big actual method for finding antiderivatives or definite integrals, which was U substitution. That the integral of f of g of x times g prime of x is equal to the integral of f of u du, where u is equal to g of x. Kind of like our reverse chain rule for integrals, basically. And notably, antiderivative slash indefinite integrals are mostly interchangeable. Where the integral of little f of x dx is equal to big F of x plus some constant, where big F prime of x is equal to little f of x. Right. Whenever you write that indefinite integral, you're just saying you're finding sort of the global antiderivative, right? You're finding an antiderivative and then saying, all right, it differs by some family of constants. So that was most of the technique stuff we did. We didn't do that much technique with integrals because you just don't have time in calculus 1. You will kick off calculus 2 with some more techniques of integration. Integration by parts, trigonometric substitution, partial fractions, that sort of stuff. But we did end up talking about some applications of integration. In particular, we talked about like area beneath curves, beneath and between. And I forgot to give you my activity on the Gini index, so whoops. I guess that's not going to happen this semester. Whatever. We talked about average value, f average is 1 over b minus a times the integral from a to b of f of x dx, right? As well as the mean value theorem for integrals. Which the mean value theorem for integrals basically says that every continuous function achieves its average value at some point. Much like the intermediate value theorem and the mean value theorem for derivatives, this has a stronger, like it has that mathematical statement where it's like, suppose f of x is a continuous function, then blah 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 is true. But in layman's terms, it basically says that every continuous function, if you take some segment of it and you take the average value, it will achieve that average value at some point in that interval. And then we talked about separable differential equations. So this is so a differential equation is in particular some sort of equation that relates a function to its own derivative in some form. And we talked specifically about the type that can be written as g of y dy is equal to f of x dx. So separating and integrating. And then last class, I babbled on a little bit about a couple of applications to like physics-based applications. So we had physics-based applications to work and PVA, or position, velocity, and acceleration. In particular, we spent a little bit of time discussing about how to consider position, velocity, and acceleration as a series of linked differential equations. For instance, A is equal to dv over dt, x is equal to v is equal to dx over dt, etc. And that brings us to the present. I think that is more or less our entire course. Obviously, I spent a lot more time talking about the stuff we just did rather than the stuff we have been doing for the past, 3-4 months of your life, because that's you've had a little bit less time. You've tested on the other stuff before, so you're a little more familiar with it. Um, but that's basically what we've done so far. Does anybody have any specific topics that they wanted to ask questions about? Or something that I hit on just now that you could use some clarification on? Well, sort of. Technically, you can think of the area beneath a curve being the problem where the bottom curve is just zero. Like the area between curves is kind of an extension of the geometric interpretation of an integral as the signed area between the x-axis and the function. Does that answer the question, Tyler? Mm-hmm. Yeah. Yeah, generally, if you're given two problems, if you're given two things that do intersect, yes. Sometimes you're just given an arbitrary interval and it says, like, hey, here's the interval in which you want to find the area between them, right? So you can have something that either looks like maybe like this, right? Where you're given two arbitrary endpoints, or you might have something that looks like this, where your endpoints are a little less arbitrary because they're the intersections of the two functions. F and G, F and in general, my expectation is not for you to be an expert at solving whatever random nonsense equation I send at you. For these problems to locate the endpoints, I'm pretty okay with you using technology to graph the two functions. I'm a lot less okay with you just using technology to then find the value of the integral and then just give me an answer. You do need to demonstrate all of the work that leads you to your integral and the actual answer. But you can definitely use technology to find the intersections between the curves. I don't mind that at all. Any other questions, areas of clarification? Okay. So the other thing that I wanted to try and spend our time on is does anybody have any questions from the review guide I posted last class? Um, so that I can maybe do a couple of examples for you guys so you can take a look at that sort of stuff. Okay, so did you want the ones from the actual review sheet, or did you want to look at the ones from Paul's online math notes? Okay. All right. So yeah, we can look at 2.4.4 on the final review here. So object has an acceleration given by a of t is equal to, oh, I forgot to write sine as a function. That annoys me. The sine of pi t at t equals 0.25 the object is at rest. V of 1, oh, there's a typo again, 0.25 is 1, 0. And at t equals 0, the object is 1 unit to the left. That is x of 0 or s of 0 is equal to negative 1. And we want to find the object's velocity and position functions. So a is equal to 3 sine of pi t. But acceleration is the derivative of velocity with respect to time. So we can write this as a differential equation. dv over dt is equal to 3 sine of pi t. Technically, we don't actually have to write this as a differential equation. We can just solve this by integrating, but it makes sense in the context of separable differential equations. The theory totally applies here. So we can rewrite this as dv over dt equals 3 sine pi t. We can separate this. We get dv is equal to 3 sine pi t dt. And then, so now that we're separated, we can then integrate. Oops. So the integral dv is just v, and the integral of 3 sine of pi t, technically this requires a small u substitution. It's a u substitution with constant, so it's not that big of a deal, but we should still do it. So we're going to let u equal pi t. Then du is equal to pi dt, which means that dt is equal to 1 over pi du. So this is actually the integral of 3 sine of u times 1 over pi du. So v is equal to 3 over pi times negative cosine of u plus a constant. Or v is equal to 3 over pi, sorry, negative 3 over pi cosine of pi t plus c. Does that feel relatively reasonable to everybody? Okay. So, well, we're about a third of the way through the problem. So, yeah, setting them up can be a little tricky, but just writing them as the differential equation, I think, is the big part. From here, it's going to get a little nitty gritty at this point. We need to solve for c. So now we're going to apply our initial condition, which was that v of 0.25 or 1 over 4 is equal to 0. So that means that 0 is equal to negative 3 over pi cosine of pi over 4 plus c, which means that 0 is equal to negative 3 square root of 2 over 2 pi plus c. Cosine of pi over 4 is square root of 2 over 2. So that means that c here is equal to negative 3 square root 2 over 2 pi. So we get that our velocity here is negative 3 pi cosine of pi t minus, or sorry, this should be positive, sorry, plus 3 square root of 2 over 2 pi. So that's the first part. The second part is almost exactly the same idea. Note the velocity function is dx over dt. Velocity is the derivative of position with respect to time. So we can rewrite this again as a separable differential equation. Dx over dt is equal to negative 3 over pi cosine of pi t plus 3 square root 2 over 2 pi. And then again, we can pull the dt over to the other side. So dx is equal to negative 3 over pi cosine of pi t plus 3 square root of 2 over 2 pi dt. And then we can integrate both sides to give us that. And I'm going to skip through this integral a little bit more. The u substitution for this cosine of pi t part is exactly the same u substitution it was last time. So here this will be negative 3 over pi squared sine of pi t. And for this right-hand part here, it's just a constant, so we're just going to tack on a t. 3 square root of 2 over 2 pi plus c. And then finally, we need to solve for c using the initial condition. And here our initial condition is that x of 0 is equal to negative 1. For what it's worth, I will say right now that the version of this type of problem that shows up on the test has much nicer numbers than this one does. I tried to make the arithmetic a little bit more manageable this time. That isn't to say that it's easy, just that it's more manageable. So here, negative 1 is equal to negative 3 over pi squared sine of 0 plus 3 over the square root of 2 times 2 pi times 0 plus c. So luckily sine of 0 is 0 and anything times 0 is 0, so these two terms fall off. So we get that c here is equal to negative 1. And our final answer for the position function then is x is equal to negative 3 over pi squared sine of pi t plus 3 square root of 2 over 2 pi t minus 1. And that is our position function. So the big idea behind this one, and it's the same idea I tried to sort of give to you guys last class. The big idea here is that you can consider, so the velocity is, or acceleration is the derivative of velocity, right? So there should be a way to get from acceleration back to velocity using an antiderivative. And sort of the way that I wanted to consider it rather than just using antiderivatives is I wanted to consider it in sort of a bigger sense to look at it using an integral, right, or using differential equations, so that we could consider velocities that are not only just dependent on the dependent variable, but there are lots of situations where acceleration is dependent on the current velocity. Um, for example, drag. If you're dealing with drag at moderate speeds, drag is proportional to the square of the velocity. So, in order to consider things that have an acceleration that's dependent on velocity rather than just time, you have to have a somewhat more sophisticated way of looking at things. And I think looking at them through the lens of differential equations is a very nice way to look at it. So hopefully that helped a little bit, Isaiah and everyone. Are there any other specific questions that people would like to see? On the review sheet? The Riemann definition of the integral there? Okay. So we're going to do Riemann integration here. And that means that we're going to apply our definition, right? That the integral from a to b of f of x dx is equal to the limit as big N goes to infinity of the sum from little n equals 1 to big N of f of x sub n times delta x, where delta x is equal to big N over b minus a. This is the width of each rectangle in a Riemann sum, right? And x sub n is equal to a plus n delta x. So in this case, the numbers are actually quite nice. Well, they're nice enough anyways. We have the integral from 0 to 3 of 3x plus 2 dx is equal to the limit as n approaches infinity of the sum from little n equals 1 to big N of, so delta x is going to be n over 3. It's big N over b minus a. B is 3, a is 0. Then x sub n will be 0 plus n times big N over b minus a. Wait. I'm really stupid. This is the reciprocal. It's b minus a over n. So, any of you guys that were scribbling down notes earlier, go back up to your section where I gave the definition of Riemann integration and fix this: the delta x equals n over b minus a. It's supposed to be the width of each rectangle, which is the width of the total interval divided by the number of rectangles, not the number of rectangles divided by the width of the interval. So Make sure that that is not incorrect in your notes, otherwise you're going to have some trouble. So this would be, x sub n would be 3 little n over big N. So our limit here ends up being 3 times 3 little n over big N plus 2 all times 3 over big N. I'm just taking the function here, which is 3x plus 2, and I'm taking the x out and replacing it with x sub n, 3n over big N. So this is the limit as big N goes to infinity of the sum from n equals 1 to big N. Let's simplify this out a little bit. We can distribute this 3 on the inside here. We get 9n over big N plus 2 times 3 over big N. And then we can distribute that as well. So it's the limit as big N goes to infinity of the sum from n equals 1 to big N of 27 little n over big N squared plus 6 over big N. And then we need to do some summation jujitsu here. We're going to need to split it up and pull everything that we can out so we can just apply our formulas. So first things first, we can split the sum over these two sums, right? Basically, because we have something plus something, it doesn't matter what order that we're adding up all these terms in. We could add up all of the first terms first and then add up all the second terms. We don't need to take them in order. So we can rewrite this as the limit as big N goes to infinity of the sum from n equals 1 to big N of 27 little n over big N squared plus the sum from n equals 1 to big N of 6 over n. This second sum is actually pretty easy to deal with, right? It's just going to be whatever big N is, it's going to be 6 over big N times big N, right? Because we're just taking, if big N was 8, then we would be taking 6 over 8 and adding it to itself 8 times, right? So over here, we're just going to get 6 over big N times big N. And those big N's will definitely cancel for us. The right-hand sum is a little bit trickier. We want to pull out everything that's constant according to the sum. By the time we get to this sum, big N will already have been chosen, right? We need to know what big N is before we can hope to add up big N copies of whatever number this is. So n squared and 27 can both pull out in front of this sum. So that'll be 27 over n squared times the sum from n equals 1 to big N of just little n. And now we can apply our summation formula, right? We know that the sum from n equals 1 to big N of little n is equal to n times n plus 1 over 2. Sorry, those should be big N's, not little n's. So we get the limit as big N goes to infinity of 27 over big N squared times n plus 1 over 2 plus 6. or the limit as big N goes to infinity of 27n squared plus 27n over 2n squared, all plus 6. And now at this point, I hope the limit is relatively straightforward to apply. As n goes to infinity, the only thing that's going to matter in this fractional term is the squared parts, right? This 27n will become meaninglessly small. So we end up with the limit as big N goes to infinity, or well, we end up evaluating the limit to get 27 over 2 plus 6, or 39 over 2, which is about, what, 19.5? This one should be somewhat easy to check just using simple geometry, right? We could do an antiderivative as well, so let's check that using the fundamental theorem first. The integral from 0 to 3 of 3x plus 2 dx should be equal to 3x squared over 2 plus 2x evaluated between 0 and 3. So that'll be 3 times 3 squared over 2 plus 2 times 3 minus 3 times 0 squared over 2 plus 2 times 0, which is 27 over 2 plus 6, which is 39 over 2, or 19.5. And if we look at it by geometry, it's a line that has an x-intercept of 2, right? And by the time it goes over to 3, this point here is the point 3 comma, it has a slope of 3, so that should be 11, right? So this is a trapezoid with h1 of 2, h2 of 11. So the area of that trapezoid is 2 plus 11 over 2 times 3. Which is 13 over 2 times 3, which is 39 over 2, or 19.5. So 3 different ways of doing that integral: Riemann integration, fundamental theorem of calculus, and geometry, and all 3 of them agree to be the same exact thing, which is good, because if it didn't, then we'd be in trouble. Is that what you were looking for, Ilsa? Okay, cool. Any other problems that people want to see? 263. I'm going to pin Katie's comment. Ooh, wait, what? There shouldn't be any... I'm not sure what you mean by it's going to use chain rule. Well, it's not a derivative, right? You're not taking derivatives to solve differential equations. But yeah, we can definitely do one of those. Give me just 1 second. Let me pull one up. So like 2.3 stuff here. Yeah, let's just do the first one here. So we're gonna so dy over dx is equal to 3xy. And we're find the general solution to the diffq. So this is a separable differential equation, because every differential equation I hand you is going to be separable because you don't have the tools to deal with anything more sophisticated. So we can rewrite this as dy as 1 over y dy is equal to 3x dx. So when you're separating these, you're not actually these look very similar to related rates. And in some sense, what we're doing here with separable differential equations is we're kind of undoing related rates problems, right? But once you have it separated like this, you have all the y's on the left-hand side with the dy, all the x's on the right-hand side with the dx. All that remains is to integrate. So the integral of 1 over y dy is equal to the integral of 3x dx. So on the left-hand side here, this is ln of the absolute value of y is equal to, on the right-hand side, we end up with 3x squared over 2 plus a constant. Then we can do e to the power of both sides. So the absolute value of y is equal to e to the 3x squared plus 2 plus c. And then we can end up with y is equal to plus or minus e to the 3x squared over 2 plus c. Or if you prefer, this plus c can come out front since it's plus e to the c, or times e to the c. So this is really just c e to the 3x squared over 2. For what it's worth, both of these answers are perfectly acceptable. I'm not going to get particularly picky. If this was a differential equations class, I'd want you to make sure you give me this right-hand one. But if it was a differential equations class, you guys would have done at least one extra semester of integration on top of what you already have. So we can definitely stick with either of these being valid for Calc 1. Well, so c is an arbitrary constant, right? So it could be positive or negative. Yeah. Technically, when we pull it out, it's like plus or minus ce to the 3x squared over 2, where c is strictly positive, right? Or rather, c is greater than or equal to 0. But that doesn't. When we just put the plus or minus in, we just get any arbitrary constant. So typically, the plus or minus gets suppressed at that point. Yes, they are not related rates problems. Please be sure to read the instructions extremely carefully on this exam. There are a lot of different problems that look like other problems, and you need to make sure that you are doing the correct type of problem for every problem. Incidentally, there is one problem on this test. Well, it's technically two problems that they're going to feel very scary because they have a lot of words in them. I would like to try and encourage you guys to try those two problems. They are actually not particularly difficult problems, and I give you the answers for the problems inside the problems themselves, so you're just showing the work. Like they're basically saying, show that this turns into this. So I would really love it, and I think that it's a good idea for you guys to try those problems rather than just taking the typical tack of saying, oh, I'm going to cross off the problem that has the most words on it, because that's usually what I get, and it always makes me very sad because generally the more words a problem has, the more clever I felt when I was writing it, and then I get very sad when everybody crosses it off. So I'd appreciate it if you gave it a try. Obviously, you do not have to do that problem. It's like problem. It's either 9 and 10 or 8 and 9. I think it's 9 and 10, but you'll know what I mean when you see it. I promise it's not undoable. Okay. It's about 1 o'clock, which is about where I planned on ending this. Does anybody have any problems or questions that they desperately want to ask before I give you guys the test and let you guys go? Oh, so yes, good point. The exam is due. I think I did mention this, but exam is due on the 12th at 2:35 p.m. So we don't technically have class because the Tuesday Thursday classes don't have class. It's just the Monday classes, but it is when our class. It is at the end of when our class would have been on the 12th. Um, so that gives me about a little less than 48 hours to grade everything. So it should be okay. Any other questions, burning and important or otherwise? Okay. Before I let you guys go, I want to thank you guys. I know this semester has not been the ideal way that we all wanted to learn or teach Calculus 1. But I think that you guys have been a really great class. I really appreciate how much effort and energy you guys have put into embracing the remote stuff. I know that it wasn't the thing that you were looking forward to, but I think that it hopefully turned out in a way that people were able to get the content they needed. So thank you for putting in the energy, putting in the time, um, and hopefully everything goes well on this final, and everything goes well on your journey from this point forward. So I hope you guys have a wonderful rest of your semester and a wonderful rest of your schooling time, and I will hopefully see some of you around here and there.